Welcome back to Chemical Process Safety. As we conclude the semester, I wanted to make a video that was pretty short and on personal and laboratory safety. All throughout the semester, we have been focusing on process safety, which I explained in one of the very first videos of the course, which is about preventing the big stuff, the stuff that has a low probability of happening, but if it happens, it could be catastrophic. And I made the point of distinguishing process safety versus personal safety. Personal safety, in contrast, focuses on the stuff that is higher likelihood of happening, but the consequences could be far less severe. And when I say far less severe, I don't mean absolutely without consequence, because you could still get seriously injured or harmed. It's just that it would be only one person getting injured or harmed as opposed to, multiple in the case of an explosion. So these two concepts are distinct, but both of them are important to talk about. And as we start the last module of the course, again, I wanted to briefly mention personal safety as well. So one of the first things you want to do when you're actually working with stuff in the research lab or in the unit ops lab is to make sure that you have fully read the standard operating procedure to the extent that you're able to. Reading SOPs the first time is a bit challenging because when you're trying to read a document without the piece of equipment in front of you, sometimes it can be hard to envision the steps that are involved. But you should at least make an effort into locating the SOP and trying to imagine what actually operating the piece of equipment is going to be like. You should also know the relevant chemicals that are going to be in the experiment that you're running, and make an effort to look up the SDSs or the safety data sheets to investigate some of the hazards. And then for me, anticipation is one of the key things that you can do to prepare. I've mentioned before in this class that in my personal life, I am an optimist. I am not programmed, I'm not wired to think about the worst case scenario. But ever since teaching this class and ever since having this different perspective, I've let this kind of come into my personal life where if I'm in the car and my son is in the back seat, for example, I'm always on the lookout for like what sort of thing could happen or what sort of situation might arise where my safety or his safety would be put in danger. Like if I'm approaching an intersection, I'm always looking out for somebody who might be running a red light from the other side, and anticipating that that could happen so that I could respond proactively. So specifically in our unit ops lab currently, the chemicals that are involved are acetone, 2-butanol, carbon dioxide, helium, diatomaceous earth, ethylene glycol, isopar M, isopropanol, and methyl ethyl ketone. And as you start the unit ops lab, you will be given these SDSs. And if you're not given them, you have the ability to look them up on your own. I mentioned a standard operating procedure, but I also recognize that it means something specific and that may not be well defined or well understood. So just to quickly define what an SOP is, this means a series of step-by-step instructions for performing a task or operating a piece of equipment. Even though the name standard operating procedures kind of sounds like it would be the same across all contexts, it's not, right? It's going to be specific to your lab or to the specific location that you're performing the work. In other words, let's say that you have the same exact piece of equipment. When I was in grad school, we used a confocal microscope. And we had a certain SOP for operation of our confocal microscope. But if that same confocal microscope were in a different lab with a different context, the SOP might look different. So that's the point that I'm trying to make. And while you should absolutely understand the SOP, you should absolutely not assume that the SOP is infallible, especially if you are in an academic research lab where the author might have been a grad student. I know personally when I wrote SOPs when I was in grad school, there were unanswered questions, right? I was not the overall expert on every single aspect as to what was going on. The SOP can be changed and should be continually revisited over time and updated to answer some of these unanswered questions. So when I was writing an SOP, I would approach it as it was sort of like a more formalized version of my lab notebook, where I was talking about my expertise in using the piece of equipment, understanding what works well, what doesn't work well, and what I knew about safe operation of that piece of equipment. Um, But yeah, if you have access to that author, I think it's a great idea to ask questions and suggest changes. And if you don't have access to the author, you can still suggest changes or amend the SOP as necessary. Um, Examples of what I'm talking about when you read an SOP, I'm thinking back to my own experiences, my first couple of weeks in my research lab. It would say something like, turn the equipment on. And my question would be like, okay, well, where's the switch, right? A good SOP requires diagrams, pictures of the actual equipment with callouts, with annotations. And sometimes the author might overlook that, right? If you've been using this piece of equipment every day for the past 3 years, you might think it's completely obvious where the switch is, but a newcomer might not. So again, this is what I mean by the author might overlook small details. And that's why it's important that even as a newcomer, you're asking questions that might seem obvious at first, but actually can be very important to clarify. Okay, safety data sheets. Honestly, what I do when I want to find it is I just Google the name of the substance and then SDS to the end of that. And typically the manufacturer like Sigma-Aldrich or Fisher Scientific will have an SOP that's published. Really what I'm looking for when I look at an SOP are the specific hazards of that chemical, the reactivity, and what type of first aid and accidental release measures I should take if there was to be a spill. All chemicals in the area should have the SDS read for it, not just the one that you are specifically going to be working with. An example would be, I don't know why you would be doing this, but if you were working with a particular acid, right, and you only looked at the SDS for that acid, but let's say there was also a base that somebody else was using for a different experiment, even on the same bench, you need to be conversant in that as well. GHS pictograms are also going to be present on the SDS, and I think just in general, all chemical engineers should have these memorized by heart. You'll see these on bottles of chemicals. Health hazard, flame, exclamation mark means it's a skin irritant with acute toxicity. Gas cylinder, corrosion, something explosive, an oxidizer, environmental hazard, or acute toxicity. So anytime you see one of these icons, you should be immediately aware of what that icon means. The NFPA diamond is another one that you've undoubtedly seen in real life several times, but might not have internalized what it means. But again, this is something that all chemical engineers should know. If you see, even around campus, for example, you'll see storage tanks of chemicals that'll have this NFPA diamond on it. If it shows all zeros, that is a very relatively safe chemical. The NFPA diamond goes in increments from 0 to 4 for 3 specific hazards, and then there's like a wild card hazard down at the bottom here. So blue is the health hazard. 0 again is going to be completely safe, ranging up to 4, which is extremely deadly. If you ever see a 4 just walking around in everyday life, I'd probably make sure to steer clear from whatever that tank is. Hopefully, civilians don't have access to that sort of chemical, but again, something to watch out for. Red is for flammability, and this is quantified on a scale relating to flashpoint, which we now know what flashpoint exactly means from a definition perspective. 0 again means it will not burn at all, ranging up to 4 with a flash point below 73 Fahrenheit, which is approximately room temperature-ish. Yellow is chemical reactivity, or instability is another way to look at that, where 0 is not reactive at all, 4 is highly, highly reactive and might detonate. And then the white square at the bottom is for a specific hazard. So this is a dashed line, meaning there is no specific hazard, but you might see OX, which stands for oxidizer. And that's an indication that it probably shouldn't be kept around a fuel, for example. Acids, bases, corrosive, water reactive, or radioactive are others that you might see in this space. You have to be very careful and never assume that the number is always on a scale from low to high. So here's what I'm talking about. 0 on the NFPA diamond is safe, whereas 4 is very hazardous. There's a separate set of labels called the HAZCOM labels, where they basically flip it. And this is a terrible, terrible convention that hopefully will be changed in the near future. But in the HAZCOM labels, 4 is least severe, ranging up to 1 being most severe, which is counterintuitive and it doesn't make sense to me at all. And I think most things from a safety perspective should be intuitive so that in a pinch you can understand what's going on. But again, this is just something to be aware of. Anticipating emergencies. When you're in the lab, be that a research lab or the unit ops lab, you should know the escape routes. If something happens, what is the fastest way outside and what route or what path should you take to get there? What are the emergency phone numbers? And even if you don't have these by heart, you should know where to find them. So obviously 911 would be the quickest example, but you might want to contact somebody else before that. Also knowing where the first aid and the spill kits are, safety showers, eye wash stations, etc. When an emergency happens, you don't want to be stopping and pausing and asking the question, where are these things and how do I use it? These are all things to think about and to have questions for before you even start the work. All right, let's talk about PPE specifically in the lab. Gloves are one potential piece of PPE that you will most likely encounter. But I want to make the point here that not all gloves are created equal and different types of glove have different purposes. So over here on the left, we've got heat gloves or flame resistant gloves. These are obviously for when you're working with something that's very, very hot. On the other side of the spectrum, in the middle, we've got cryogenic gloves, which are good for working with something very, very cold. And even though both of these are well insulated, they have different properties. So I like the intuitiveness with which these have been designed. I like the orange ones for heat. Orange is a very hot color, so it makes sense that you would grab the orange ones for working with something hot. Blue is a cold color, makes sense for working with something cold. However, you should be very careful never to use color as the reason why you pick up any particular gloves, because nitrile gloves, this is a misconception. They come in many different colors. Purple, blue, and pink are common ones. I've also seen green ones. The color of nitrile gloves have absolutely nothing to do with which chemicals they're compatible with or anything like that. It's just simply cosmetic. In addition to nitrile gloves, there's also latex gloves and vinyl gloves. You should be aware, for example, if you have a latex allergy, whether or not your lab uses latex gloves and potentially think about what are the alternatives for those. But these different types of gloves will have different resistances to certain chemicals. So again, depending on what you are working with will influence the type of glove that you should be using. This should not be your decision, by the way. When you start working in a lab, you will probably have SOPs to work off of, and that SOP will tell you, ideally it would tell you exactly what type of glove you should be using for what you're going to be working with. But as you get more established into working with labs, and as you start thinking about writing your own SOPs maybe someday, or developing your new procedures, you definitely have to think about glove compatibility at that point. There are certain rules to using gloves, nitrile gloves specifically, that I'm thinking of. And that is that you should never be using these gloves in the hallway. Sometimes when you're in the research lab, you'll have multiple different rooms that you might need to be working back and forth between. So it's a very bad idea. You should never be using your gloved hand to open doors or to open the elevator or to use a stair rail or to go to the bathroom or to go to the water fountain or anything like that. And even if you just put the gloves on and they're completely clean, it's a bad optic, right? If a passerby were to see you operating a door with a glove on, for example, they might think that that is an acceptable thing to do. And it's not. So always take at least one of your gloves off and use that hand to operate the doors and the elevators and whatever you're using. And then if you have samples, you can use your gloved hand, the other one, to carry those. Gloves are very, very cheap. I remember I used to like to skimp as much as possible, and I'm not a very wasteful person in general. But safety PPE is not the time to think about wasting gloves. If there's a hole in your glove, for example, always make sure to replace it immediately. Don't be like, oh, I'm just going to finish up my procedure and it's not a big deal. Always replace your glove. And don't be shy about replacing your gloves frequently, especially if your hands tend to sweat or anything like that. Safety goggles is also another important and common one. Anytime you're working with chemicals or others are working with chemicals, definitely want to make sure you're using your safety goggles, even when it's hot and humid outside and they tend to fog up. Safety goggles can be comfortable if you get the right ones. And hopefully they're not falling off your face. But I tend to like the ones that are form-fitting, that kind of wrap around my head and get good side protection as well. Lab coats and FRCs you might see as well, probably more so lab coats, and you might see FRCs if you're an internship. But the difference is that FRCs are flame retardant coveralls, is what that acronym stands for. This is basically just a larger lab coat with the extra flame retardants built into it as well. So if you're working with something flammable, FRCs are going to be preferable over lab coats. Hard hats in the unit ops lab, you'll be wearing these. These are useful anytime there's a possible danger of something falling from above. So the unit ops lab is 3 floors, and there's an open part of the lab where something from the second or third floor could potentially fall down to the first floor. So anytime there's a risk of something like that, hard hats are necessary. And then compressed gases. You will be working with compressed gases in unit ops, and you might be working with compressed gases in your research labs. There are 7 hazards that are associated with these. So pause the video now and play Family Feud. See if you can guess which the 7 hazards are. Just to quickly go through them, we've talked about some of these as we've gone through the course already. But the fact that they're under extremely high pressure is the most obvious hazard, and there's a risk of rupture anytime something is at a high pressure like that. Depending on what the gas is, it could be an asphyxiation hazard. So even if it's nitrogen inside that gas cylinder, that could displace oxygen if it were to be if there were to be a leak in that gas cylinder. You would not be able to breathe properly. These gas cylinders are very heavy. You definitely would not want one to fall down and hit your foot, for example. And in my experiences, they also tend to be top heavy as well. So with a very high center of gravity, there's a tipping hazard as well. Depending on what the gas is, it might be flammable, it might be toxic, it might be reactive. And if you ever worked with a gas cylinder, you know that when you throttle something that's at a very high pressure into a low pressure, the temperature tends to decrease very well. So it could get very cold, especially on the regulator, and that's a hazard in and of itself. Transporting gas cylinders is a whole nother thing entirely. This person is doing it correctly. There are oftentimes special dollies that are made for transporting gas cylinders, and notice how this person has the cap firmly attached to the valve. It's belted, and nothing looks unstable about this. So this is definitely the best way to transport a gas cylinder. Also, the regulator is taken off. So if you've never worked with one of these, the way that you will put it into service, if this one's on the wall, for example, you'd take the cap off and you'd put the regulator on, and that would be connected to whatever you're supplying with this gas. This is what the regulator looks like. The one that's closest to the valve is going to be the internal pressure, and the one that's furthest away is going to be the outlet pressure. And you can adjust this handle to be basically whatever outlet pressure you want. This is incorrect ways to store gas cylinders. So these don't have belts, notably. But anytime the cylinder is belted, if it's in use, you can have the cap off with the regulator on, but if it's out of use, you want the cap to be on. And that's basically a rule. If the cap is off, the belt must be on. And the reason why is that this is a very mechanically weak part of the gas cylinder. And if the cylinder were to tip over, this valve is at a risk of shearing off, and basically you can create a torpedo with this gas cylinder. And then finally, to wrap up, I'm going to ask that you watch this video. I'll have a link to this in the module. But this is basically 3 separate safety incidences which occurred all in academic laboratories and can show that academic research is not necessarily safe and it requires vigilance at all times. And that'll conclude this video. Hopefully that was entertaining and gave you some more things to think about. See you next time.